Hi Mindsetters, and welcome to Mindset Learn Extra, and this is grade 11 science. Tonight's show is brought to you by Liberty, and last week we covered kinetic theory of gases with Bruce. And tonight our topic is gas laws, and Bruce will be taking us through it. Hi Bruce, how are you?
I'm very well, thanks, Indy. Yes, guys, we're going to be looking at gas laws. We looked at the kinetic theory last week. This week it's the gas laws. Bit mathematical, lots of theory involved. So guys, make sure you have a pen and pencil ready. Calculator as well, so we can do a couple of questions and a few problems together. And don't forget to send in your questions through Twitter and Facebook, and I'll see what I can do with them.
Fantastic. Thanks, guys. Okay, guys, so please make sure you only post questions on our wall that are relating to this topic. If you are stuck, stick with us throughout the year, and we'll eventually get round to the section you're having difficulty with. Next week, our topic will be gas laws again, and lots of you have been asking us about our schedule. So if you are in a study group, the topic next week is gas laws. The show tonight will start off with a lesson on gas laws, like I've said, and then after the break, we'll be working through an example or two. Then, lastly, we'll be tackling your questions on this topic on our page in the last 15 minutes of the show. The way to get hold of us is on our Facebook page, facebook.com/learnextra. Our Twitter handle is @learnextra. So while you are watching, shoot questions off to us, and we'll get round to them in the third part of the show. Guys, I have a Casio calculator to be giving away. The best post on Facebook, we will be announcing the winner tomorrow on the page. So check the page tomorrow, guys. And after the break, we'll be back with Bruce. Hi guys, and welcome back to Learn Extra Live, grade 11. I hope that you're all tuning in and you're ready for Bruce and you're ready to learn more and learn extra. So guys, we're chatting about gases. Get those questions in on the page. Please make sure that it is only referring to what we're talking about. It'll make us much, much quicker to get through those questions towards the end. Okay, Bruce, over to you.
Great, Indy. Thanks very much, guys, and welcome to today's show. I'm sure a lot of you actually were tuned in last week, and you'll remember that I went through the whole basics of the kinetic theory of matter and then applying the kinetic theory of matter of gas, or kinetic theory of matter to gases, and we came up with a couple of very important points. And I thought for tonight's show, I'll quickly run through as a revision the application of the kinetic theory of matter to gases. And what I've done here is just taken the slide that I had last week, and I'm just going to quickly run through it in terms of some of the more important points that are associated with our gases. Okay, so guys, what's the first thing we have to look at? We talk about collisions of the walls with the container, and we spoke at quite a lot of length last week about how the gas particles actually collide with the wall. They exert a force per unit area, and that force per unit area is what we call pressure. And the more collisions we have, or the stronger the collisions actually are, then the greater the pressure of the gas inside that container. If we just scroll down a little bit, you can see here that what will happen is that heating a gas will increase the average kinetic energy of the particles. Remember, guys, when we heat, we're transferring energy into the system. The more energy in the system, the faster the particles are going to move. The faster they move, they're going to collide with the walls of the container more frequently, probably a lot harder as well, and therefore you're going to increase your pressure as well. So there we go, more collisions with the walls of the container, as well as much more forceful collisions, thus increasing the pressure of the gas, and vice versa. If I just scroll down a little bit more, cooling the gas will decrease the average kinetic energy. In other words, we now withdraw energy out of the system. We actually find that we've got a lack of energy. The particles will move slower, therefore less frequent collisions, less forceful collisions, and therefore less forceful collisions are decreasing the pressure of the gas. Okay, and then we came to a couple of little theories over here. So let's pull this up a little bit more. There we go. So thus, the pressure that a gas exerts inside the container is directly proportional to the average kinetic energy of the gas particles inside the container. And remember, guys, how do we measure that average kinetic energy? Well, you'll remember we spoke about the temperature of the gas. So there, guys, in a nutshell, is one of our first gas laws, and we're going to be having a look at these gas laws a bit later, that pressure and temperature are going to be directly related. Also, we had another one I brought up last week as well. There we go. As the average kinetic energy of the gas particles increases and decreases, the particles will move further away or closer to each other. Thus, the volume occupied by the gas is going to now also depend on that temperature as well. If we have a large amount of energy, in other words, a high temperature in the system, particles have got lots of energy, what's going to happen? They're going to want to move away. They're going to want to increase the volume, the space occupied by the gas. And vice versa, if we find that we decrease the energy in the system, we lower the temperature, the particles are going to move more slowly, they're going to come closer together, they're going to decrease the space occupied by the gas, and therefore the volume of the gas will also decrease. So guys, what we also have here, just to quickly conclude our little revision slot here, is that volume is also directly proportional to temperature as long as the overall pressure in the system is going to be constant. So guys, last week, and with our quick revision now, what have we looked at? Well, we've looked at already some basic understanding of the gas laws. So what I'm going to do now is move over to looking at these gas laws in a little bit more detail and have a look now at how we can actually interpret them graphically, okay? Look at how we can interpret them mathematically. There's some small mathematical equations we have to develop. Guys, not very hard, so don't be scared. We're not going to go into some really sort of difficult maths, but very important stuff. And if you get questions on this in your exams or tests that come up, I'm sure you guys will be able to score really good marks in this particular section. Okay, so let's go and have a look quickly at our next slide. And I brought them up over here. And I've put it under a heading, the gas laws. And we are going to consider 3 gas laws in this section. The 2 gas laws we've spoken about already in some format. We spoke about the relationship between pressure and temperature at constant volume. We're going to talk about that a bit later. We've spoken about volume and temperature at constant pressure. We've also introduced that a little bit. But we're going to kick off now with our first gas law, which allows us to look at the relationship between the pressure of the gas and the volume that that gas is going to occupy. Okay, so what are we going to have a look at? Well, that law, what I'm going to call the first gas law, is called Boyles Law. Okay, it's named after an English scientist by the name of Robert Boyle. And guys, the interesting thing is that this relationship is not something that's particularly new. Robert Boyle lived in the 1700s, and that's well over 300 years ago. And already 300 years ago, he was able to establish a relationship between pressure and volume of the gas. In other words, how big was the pressure compared to the volume that the gas occupied, or vice versa, depending on what the volume that the gas occupied, how great was the pressure. That he did at constant temperature. So in other words, he had to keep a variable constant, and that variable happened to be temperature. So he was able now to look at, I'll just get a pen here, just to get a little marking over there. We can see now our relationships between pressure and volume. So the first gas law I want to spend a little bit of time with today is going to be Boyles Law. Okay, so let's have a look now at Boyles Law, and I'm going to start off with a definition of Boyles Law over here. For a fixed mass of gas, and I'll come back to these words now because they are important. In fact, I'm going to just start to underline a couple. For a fixed mass of gas kept at constant temperature, the pressure of the gas is inversely proportional. That's interesting. Inversely proportional to the volume occupied by the gas. Okay, now let's take that definition and let's break it down into some important components. I've put here for a fixed mass of gas. Now what that means, guys, is that if we want to develop this relationship, if we want to understand how Boyle developed his ideas and thinking about gases, You have to have a constant amount of gas. We can't allow for varying amounts or valves to be opened or people to just add gases in willy-nilly. You're not allowed to do that. What you have to have are a certain amount of constant variables. And I'm sure at this stage you've spoken about experimentation at schools and various things like that, where you have looked at your controlled variables, okay, and then you look at your variables that are going to change within the system. And therefore, for a fixed mass of gas, that has to be one of your controlled variables in the experiment for Boyles Law. It has to be measured at constant temperature. So in other words, we cannot allow temperature to influence the results. Why is that? Well, remember what temperature is a measure of? It's the average kinetic energy. And we know that temperature affects pressure and volume. We spoke about that in our little revision we did 5 minutes ago. That temperature measuring the average kinetic energy is going to influence pressure, and it's also going to influence volume. So guys, we cannot allow that to get involved. We must make it a control variable. That allows us to measure the relationship in terms of pressure and volume together. And if you have a look at the screen over here, and I'm afraid it is a little bit small, and I hope you guys can focus in there, you will notice now that we have got an inverse proportionality. Can you see now that the graph shows a curve? Now, whenever we have this particular curve like that, it's always a dead giveaway, guys. When we plot, in this example, pressure against volume, it's a dead giveaway in terms of the style of the shape of the graph. It means an inverse proportionality. So, right, so I'm just going to just try and make it a little bit there. I think that might actually help a little bit more, just to show you guys whether we've got it. Okay, so what have we got here? Thus, as the volume occupied by the gas decreases, so the pressure of the gas inside the container will increase. Now I'm just going to try and get a bit of a darker pen. I'll try green, because I just don't know if this yellow is actually going to work so well. I'm just going to take that out. Let's see if I can just erase this yellow bit. Yeah, I'm just going to erase the yellow out of here. Okay, it just hasn't worked very nicely. In fact, I'll just redraw that graph, because a lot of people are backing to see it. And there we go, much better. Okay, thus, as the volume occupied by the gas decreases, so if we have a look, here's my volume axis over there. So my volume is now decreasing in that direction. Can you see now what's happening to my pressure as my volume decreases? Can you see now, if I just draw a couple of dotted lines up and across, can you see now that as my volume is decreasing, so my pressure is going to be increasing? That is a classic indication of inverse proportionality. Okay, and I've also put here a little remember note. Whoops. He's got a little bit too quick over there. Remember, the smaller the volume, the more frequent the collisions of the gas particles on the wall of the container, and therefore we're going to have a greater pressure. So as we decrease that volume and make that volume smaller, what's going to happen is that the particles are going to hit that wall of the container more frequently, and therefore we're going to have an increase in pressure. Now, what we can also do to try and make these graphs a little bit more readable is that we can now determine the inverse of one of the variables that we are measuring. And in this case, and this is a classic Boyles Law type situation, is that if we take volume and we measure, and I'll just get my pen out again, I think I'm going to have to go over this. If we go 1 over volume, okay, in other words, we measure the reciprocal or the inverse of the volume. We've got pressure over here. Okay, sorry, that's a P there. We've got pressure over there. Can you see now what happens to the graph? The graph becomes a beautiful straight line. And that straight line, you'll notice, is going directly through the origin of the graph. That straight line indicates a direct proportionality. But what is that direct proportionality? Well, it's going to be the direct proportionality of the pressure to the inverse of the volume. Remember, guys, when we just measured pressure and volume, we had an inverse proportionality. But if we take the reciprocal or inverse of one of the variables, we will get that classic direct proportionality curve or graph or straight line that goes through the origin and is a straight line that indicates that relationship. So there now, guys, is the basics behind Boyles Law, is that we have a relationship between pressure and between volume. The relationship is an inverse proportionality or a direct proportionality to the inverse of one of the variables. Okay, so let's have a look over here. Right. Sorry, let's get this thing back. Here it is. And there we got it. Thus, pressure is directly proportional to the inverse of the volume. And how do we write that, guys? Well, pressure is directly proportional to the inverse of the volume. P directly proportional to 1 over V. And that's how we represent it in a mathematical type relationship. But guys, what I want to do now is to take now this relationship, this direct proportionality to the inverse of the volume, and have a look now at how we can manipulate this to allow us to develop a mathematical equation for Boyles Law. So let's have a look now at this graph. Okay, I'm just going to extend the page a little bit. There we go. Right, if you have a look at my graph, and there it is, you'll notice now that I have drawn two gradient interpretations there. Basically, I've got one over here in black and one over here in red. Now, when we measure the gradient, a lot of you guys will remember that your gradient, okay, is going to equal the change in the y value over the change in the x value. Okay, so if we have a look at the gradient, this one here will be a change in pressure, okay, and this one will represent a change in the reciprocal of the volume. And I'm looking at the black gradient interpretation over here. So therefore, can you see now that my gradient for the black line is going to equal delta P over 1 over, sorry, delta 1 over V. And I'm going to call that the first one, so it's going to be number 1. I'm just going to put that like that. So I'm going to have delta P1 over delta 1 over V1. Okay, don't worry about any values at this stage. I just want you to follow the very simple mathematics that I'm going to be doing. Now I'm going to go to the red gradient. I'm just going to change and select that. And hopefully I've got the color. There we go. I'm going to call this one delta P2, and this is going to be delta 1 over V2. So can we see now that the gradient now is going to equal delta P2 over delta 1 over V2. Okay. And I'm going to circle these gradients. If we've got a straight line through the origin, and we know that we've got, or it represents, a direct proportionality, what can you tell me about those two gradients? Well, those two gradients must be identical. Okay, so in other words, the gradient represented by delta P1 over delta 1 over V1 must be equal to the gradient represented by delta P2 over delta 1 over V2. Okay, now what we're going to do is have a look at a little bit of a manipulation with this. Because if I take now, I'm going to go back to my green pen over here. Let's just extend the page a little bit. Edit with my finger like that. Delta P1 over delta 1 over V1 is going to equal gradient 1. Okay, I'm going to put the grad 1 to represent gradient 1. Now, what does delta P1 over delta 1 over V1 actually represent? Well, mathematically, what we can say is that the gradient is going to equal delta P1 multiplied by delta, whoops, sorry, let's get a eraser over here, make it a bit neater for you. There we go. That's going to equal delta V1. So can you see now that the gradient we can mathematically write down as delta P1 times delta V1. Let's have a look at the purple gradient. Okay, and exactly the same thing, the purple gradient. So I'm going to call gradient number 2. That's going to equal delta P2 multiplied by delta V2. If these two gradients are equal, then what have we got? We have got a mathematical relationship where delta P1 multiplied by delta V1 must equal delta P2 multiplied by delta V2. And then all we have to do, we can clean it up by removing the deltas, and we now get the expression for Boyles Law. P1 V1 equals P2 V2. So in other words, if we have a situation of pressure and volume, and we change that situation of pressure and volume, let's call it to a second type of situation, the product of the pressure and the volumes of each situation must equal each other. Why? Because they are going to represent a constant value. Okay, and that, guys, represents our Boyles Law gas law. Very important one. They ask a lot of questions on Boyles Law, and they are going to ask you to write down that relationship of pressure and volume together. Okay. Well, guys, I hope that's Boyles Law done. Indy, is there time just to do another gas law quickly, or do you need a break?
I think that we're going to go to a quick ad break, and then we do, guys, I know that you're all asking questions. Remember, the last 15 minutes of the show will be left for you guys for all those questions to be answered. So what we're going to do is we're going to go to a quick break, and as soon as we get back, Bruce will be going through another law. See you then. Hi guys, and welcome back, Mindsetters. Get those questions in. Don't forget, we'll be answering your questions towards the end of the show. Bruce is going to be going over Charles's law. So Bruce, take it away.
Great, thank you, Indy. Yeah, guys, before the ad break, I went through in quite a bit of detail looking at Boyles Law, the relationship between pressure and volume at constant temperature, and we were able to derive a mathematical expression for Boyles Law, where we looked at the product of the pressure and the volume, okay, and the product of the pressure and the volume related to each other. Remember that your pressure and your volume are inversely proportional. We were able to develop a little mathematical expression. We're going to come back to those Boyles Law type calculations. We're going to practice some calculations just now, but I do want to introduce the second gas law. We have mentioned this guy already. His name is Charles, and he was actually in the 1870s, was able to develop a law that associated our volume of the gas occupied and the temperature. Remembering we had to keep one of our variables constant, and it was under constant pressure. Now, we spoke about that when we developed our kinetic theory of gases, and it was in my little revision package that I had a couple of minutes ago. So this shouldn't be different or too strange to you, but I just want to go through it again, making sure that we have got the mathematics right, and we're going to look at the interpretation of how Charles's law actually works. So Charles's law is basically defined as the volume occupied by a fixed mass of gas, and guys, there is that, whoopsie, there's that fixed mass of gas, once again, kept at constant pressure. So there, guys, again, we've got our variables, our two fixed variables, fixed mass and constant pressure. This time is directly proportional to the temperature, or what we're now going to introduce called the absolute temperature. And I'm going to spend a little bit of time having a chat with you guys as to what we mean by the word absolute temperature in a couple of minutes. But before we do that, I just want to have a look at the graph that we've got. So there we've now got the volume and we've got the temperature. Okay, so I know we're battling with to actually see this. So temperature is basically put onto the x-axis. The volume of the gas is placed onto the y-axis like that, and we have got a direct proportionality. So in other words, we have a straight line defining the relationship between volume and temperature, and that straight line is going to pass directly through the origin. That makes it directly proportional. So what does it mean? Simply, as temperature goes up, so as we move temperature and we increase temperature in that direction, can you see now that my volume is also going to be increasing as well. Now, before we go and develop this mathematically, and we can do very much the same as what we did with our relationship with Boyles Law, I want to talk a little bit about this word absolute temperature. So first time we've really mentioned absolute temperature, all we've been doing so far is talking about temperature as the measure of the average kinetic energy within the system. That is true. There's going to be no change in that theory. However, we're going to introduce you guys to a new temperature scale. And that's what I want to have a little chat about now in this section. Okay, and just to try and get this thing to move a little bit quicker, we're going to ask ourselves the question, what is absolute temperature? And the answer is actually quite simple. The absolute temperature scale, which is also known as the Kelvin temperature scale, is said to be the point where all energy in that system has been removed. So what's basically happening is that we've got a point, a temperature, where theoretically all energy in the system has been removed. That temperature we have measured as minus 273.15 degrees Celsius. That's a theoretically calculated value. Have they ever got there? No, they haven't. But they know that that point does exist. Now, on the new scale, the Kelvin temperature scale, or the absolute temperature scale, that is given the value of 0 Kelvin. Okay, 0 Kelvin. So in other words, my reference point in terms of temperature has now shifted all the way down. Okay, oops, get this up again. My reference point has shifted from my Celsius scale, so minus 273.15, to a Kelvin scale of 0 Kelvin. And we write it as 0 K. I know it looks like OK, but it's not. It means 0 Kelvin. Okay. Now, who developed this? Well, the Kelvin temperature scale was named after Lord Kelvin, who was a British scientist. And he developed this scale in the 1800s. And whenever we deal with gases, we only use the Kelvin temperature scale. And guys, that's very, very important to note. We are very used to using a Celsius scale. So when we walk outside and say, wow, it's hot, people say, well, it's about 35 degrees Celsius. Okay, that's fine. That's why everyday living and going about. However, when it comes to gases, we have to make sure we use the Kelvin temperature scale. Which means, guys, we've got to do a conversion. We are going to have to be able to convert Celsius into Kelvin. And we're going to call that the absolute temperature conversion. And I have got a little slide over here for you guys to show you how we're going to actually convert into Kelvin. So, still with Charles's law, we're going to be looking at converting Celsius temperature to Kelvin temperature. And we have this very basic equation over here. Capital T, which stands for my absolute temperature, okay, in Kelvin, is going to be 273. Now, that's the 273 which was given as my base temperature of, we had minus 273 at 0 Kelvin, plus small t. Small t represents the temperature in degrees Celsius. And that's my little conversion. Now, let's see how it works. I've got an example here for you guys. It says the temperature of a gas, the room temperature, is 25 degrees Celsius. What is the temperature in the Kelvin temperature scale? Well, guys, if temperature is 25 degrees Celsius over there, and we apply our formula, T equals 273 plus the Celsius temperature, all we do, guys, is add the two together, and guess what we get? We get a temperature of 298 Kelvin. So, very simple, very important though. We cannot ever use Celsius temperature in a gas law calculation. So please, I know I'm repeating myself, but it's one of the most important fundamentals that you must learn. Okay, I think I've got another little problem over here. Let's try it again. Yeah, example number 2. A gas is kept at a temperature of minus 198 degrees Celsius. What is the temperature on the Kelvin temperature scale? So there's my Celsius temperature, minus 198. There's my formula, T equals 273 plus the Celsius temperature. So 273 plus minus 198 comes to be 273 minus 198, and we get our answer of 75 degrees Kelvin. Okay, 75 K. Okay, right, guys. I think that's what we've got there. And what I can now do is have a look now at Charles's law a little bit mathematically, like we looked at Boyles Law. And I've got exactly, in fact, I think I've got a better slide of that over here. No, that's not that one. No, I'll keep it on this, it'll be fine. No problems. Okay, let's find that slide again. Right. Guys, can you see now? There's my volume and temperature. There's my straight line through the origin. There now I'm starting to look to plot the gradient. So let's have a look now. Again, let's pick up a pen and let's look at my gradient. Well, there's my y-axis, which is delta V. Here's my x-axis, which is delta T. And therefore my gradient is going to equal delta V over delta T. But what I'm going to do now is include a second gradient, just like I did with Boyles Law. Let's try and get my pen back. No, I don't want that. I want that. I'm going to do it in green. And I'm just going to put it in over here. There it is. And I'm going to have my delta V and my delta T there exactly the same way that I did with Boyles Law. And I'm going to write my green gradient, which is going to equal delta V over delta T. And what I'm going to do is assign numbers to them as well. So I'm going to make this the number 2 gradient. So I'm going to put the gradient number 2 is going to be delta V2 over delta T2. And the purple gradient I'm going to put over here as delta V1 and delta T1, like that. Now remember, guys, what did we say? Straight line graph, direct proportionality. The gradients must be equal. And if the gradients are equal, then gradient 1, purple gradient, and gradient 2, the green gradient, must be equal. So therefore, what we can do is write delta V1 over delta T1 must equal delta V2 over delta T2. Okay? And all we have to do is remove the deltas, and we now get a small but very simple and effective mathematical expression for Charles's law, which allows us to calculate volumes and temperatures within that relationship. V1 over T1 is equal to V2 over T2. And there now is our mathematical relationship for Charles's law. So guys, there are 2 of our gas laws that we've now developed. We spoke about the third one, and that was the relationship between pressure and temperature. And again, if you remember back, what was my relationship? Again, it was another direct proportionality. So what I'm going to do quickly is just draw those graphs up. I'm going to extend the page a bit more. And if I had to draw a graph, and I'll do it very quickly like that, and I put pressure onto my y-axis, I put temperature onto my x-axis, we said right in the beginning we have a direct proportionality between the two, and therefore, can you see, guys, we've got a very similar type of situation. So I'm just going to draw my gradients like that. This time we're going to have delta P against delta T on my gradients. Just to get my color coding going. Delta P again and delta T. And therefore, what have I got on my yellow gradient? I'm going to have, in fact, I'm going to have delta P1 over delta P2. Sorry, not over delta P2, over delta P1 as well. Let's get rid of that. It's over delta T1. It'll be gradient number 1, so it's T1 and P1. And then I'm going to go to my purple gradient, which is going to equal delta P2 over delta T2. And guys, almost as if we, whoops, a little bit too much, almost as if we're doing exactly the same thing that we did with Charles's law. The gradients must be equal, therefore delta P1 over delta T1 must equal delta P2 over delta T2, and that allows us now to remove the deltas. P1 over T1 equals P2 over T2. And there, guys, we have developed the mathematical expression for all three gas laws. Okay, Boyles Law, Charles's law, and the relationship between pressure and temperature. Okay, I've done that one quite quickly. And a quick question I'm going to throw out to you guys. If pressure and temperature are going to be our variables, what two factors are going to be our control variables in that particular question? And let's see how many of you guys can Twitter or Facebook in and see if you guys can give me the answer.
Fantastic. Guys, what we're going to do is we're going to take a short break, get your questions into that question, and we'll go through all of our questions right after the break. See you now. Hi guys, and welcome back. Can you believe we've got about 15 minutes left to our grade 11 show on gases? That's what happens when you're having fun. Time goes super fast. So guys, Bruce is going to go over a few more things in the last 10 minutes of the show. We're going through your questions, so get them in now, grade 11s. Okay, Bruce, over to you.
Right, thanks indeed. Guys, what I've done is just quickly put a little summary up on the board just so that you guys can have a look at it. My Boyles Law, which is my relationship between pressure and volume. There it is. Pressure is inversely proportional to volume at constant temperature. So my mathematical equation that I developed is that P1 V1 equals P2 and V2. Charles's law, which is my relationship between volume and temperature kept at constant pressure, is going to be V1 over T2, V1 over T1 equals V2 over T2. And then the last one we had over here is my relationship between pressure and temperature, which is P1 over T1 equals P2 over T2. There are the three gas laws, three little mathematical expressions developed. And Eddie, did we get any answers from the little challenge that I put out there?
We do. Matsi said the volume and the number of moles. Nialeti said, would it be wrong to use Celsius degrees under Charles's law? Ebenezer said temperature will be our control variable. Shakira,
okay.
going.
Let's
There's quite a few.
Who was the first person who came up there?
Okay, let me see who the first one is.
He said Mulazi, I think.
Yeah, Matsi, I think. Yes, Matsi was the first one to get the volume and the number of moles.
The volume, okay, and the number of moles. In other words, we have to keep the volume of the container constant, as well as the number of moles. The number of moles represents the fixed mass of gas. We are not going to be changing it. So guys, we must remember that when pressure and temperature vary, volume must be kept constant, as well as the amount of gas that we actually have got present in the system. So we've got to be very careful. We do not make sure we don't mix up which are all our variables and things like that. Okay. Shall we take a couple of questions, Andy?
Okay. Are you ready for them?
Right,
okay.
Let's go.
Okay, guys. While I'm talking, you can carry on sending your questions through. I will refresh. Okay, this one. Nyaleti said, would it be wrong to use Celsius degrees under Charles's law?
Yes. Unfortunately, you cannot use Celsius. You have to convert your temperature into Kelvin. Okay. If you use Celsius in the equation, you are going to be marked wrong completely. And the answer to, should I rather say, the reason as to why Celsius is wrong is because gases, we must remember, we're working off an absolute temperature scale. The Celsius temperature scale is not an absolute temperature scale. Kelvin temperature scale is. So in other words, we are going to start from our absolute zero, which we know is minus 273 degrees Celsius, but that is represented as 0 Kelvin. So therefore, we have to make sure that everything is relative to the position of 0 Kelvin. So you have to do that conversion. There's no way around it.
Okay.
It has to be done.
Well, there you go, guys. Hope you're listening. Okay, this one is from Tapiwa. And Tapiwa says, okay, what is the relationship between the volume and the temperature if the pressure remains constant?
That relationship is a direct proportionality. Volume and temperature are directly proportional. So if the pressure in your system remains constant, then what's going to happen? Remember, guys, we can vary the temperature. The temperature can either be increased or it can be decreased. Temperature represents the average kinetic energy of the particles in the system. If the particles get more energy, they're going to move faster and they're going to want to spread out. So what's going to happen is that the volume occupied by the gas is going to get larger. And once it gets larger, then your volume is going to increase, isn't it? And vice versa. If we lower the temperature, we are removing energy from the system. The particles are going to move much more slowly. They're going to come closer together. They're not going to occupy as much space. If they don't occupy as much space, the volume gets smaller. So that's why we have a direct relationship between the temperature and the volume of the gas. Here we go.
Okay, now this one is from Moaza, and Moaza says, so what experiment can we use to test Charles's law without a pressure gauge? As temperature increases, so does volume, question mark.
Okay, what you can use is what is called a gas syringe. Okay, now all you have to do is basically take a certain amount of gas, place it into a container, and attach the container to a gas syringe. I'm going to try and draw it for you, and that should give you a little bit of an idea of what you can use here. Let's just see if this thing is, here we go. So if you have a container, okay, and I'm going to just draw a container like this, okay, and it's very roughly drawn, but this container contains a fixed mass of gas, okay, and then I attach to this container over here, I attach a, remove that thing over here, attach what's called a gas syringe. Now a gas syringe is just simply a syringe. This is like a normal syringe for hypodermic, like that, okay? And that gas syringe is attached to the outlet of the container over there. And what's going to happen now is that you place this in a container, okay? And what we normally do is we fill it up with water, all right? And what we can then do is that we can either heat the water or cool the water down. It's actually much easier to heat the water. So what we normally do is we start off with ice cubes in here, okay? So it's nice and cold, okay? And we put ice cubes inside there. And what happens now is that when the water's cold, it removes the energy of the system. It lowers the temperature in the system. So the gas that's inside here is going to experience much lower temperatures. The particles are going to have much less kinetic energy. So if they're not going to really, not really going to move around, well, I seem to have lost my little object there. Let's bring it back. Sorry guys about that.
Sure, but look how quickly you just redrew that.
Okay, it's not the best looking diagram, but I think we've got the picture. Now all we have to do is place a Bunsen burner underneath. Okay, and if we place a Bunsen burner underneath and we heat with the Bunsen burner, what's going to happen now is that the Bunsen burner is going to melt the ice. Okay, and if the ice melts, what's going to happen is that energy is going to be transferred to the gas inside. Okay, and the gas particles are going to move much more quickly inside there. And what they're going to try and do is they're going to try and expand, they're going to try and increase their volume. Well, they can't break out of the actual little round bottom flask that you've got there. So what it does is that the gas particles now push against the gas syringe. And this gas syringe, what will happen is because it's flexible, like that, the plunger is actually able to move out. And on the gas syringe, you've got markings here. And those markings are markings of volume. And you can then just read off, the gas syringe. Wherever that plunger moves, you can read off the volume. And that's the volume of the gas. So you can actually measure the actual increase in volume by looking at different volume readings based on the temperature. How do we get the temperature? That's easy. Put a thermometer into the water. Okay? We can then read the thermometer off. You've got a reading from there. So you've got your temperature reading over here. You've got your volume reading. Whoops, that was a terrible V. I think this pen is getting a little tired with me at the moment. Okay, you've got your volume reading over there. There's your temperature. There's your volume. You can collect a whole lot of data, okay, like that, of volume against temperature, and you can just collect your data of volume against temperature, and once you've collected that data, all you have to do now is plot your graph, okay? And you'll be surprised as to how accurate this actually does come. Remember, guys, that temperature must be in Kelvin, okay? I'm going to actually put it there for you guys to remind you guys. But that's what we have it. Guys, unfortunately, the gas syringe is a bit of a specialized piece of equipment. Not all schools will have it. You can't just use a normal syringe you get from a pharmacy. The plunge is too tight inside the actual tube. So the gas syringe is something you have to go and actually get from a scientific distributor. But if you can get it, the experiment works very, very well. Indeed. Anyone else?
Okay, fantastic. We do have a few more. Okay, let's have a look. Tyrone wants to know, are we able to combine the laws and what do we call those gases?
Yes. Tyrone, we are going to be looking at this next week. We do combine these laws. We put them together in what is called the general gas equation. Okay? And we do that when we actually put the mathematical interpretations together. Okay? And we then have three variables. Instead of having two variables, which we measure, and two variables that we control, we now have three variables to measure, and we control one of the variables. And that variable is going to be the fixed mass of gas. And we develop what is called the general gas equation. So please, Tyrone, tune in next week. We are going to be doing those particular type of interpretations. Yeah.
Okay, so there's a few questions on the page. I know there's one from Promise, and there's one from Lorato, and there's one from Tseho, and I think it's all pretty much the same question.
Okay.
Okay, so Promise has said, what is the relationship between the Kelvin and Celsius scale in a short explanation?
Basically, all it is the difference between 273 degrees, minus 273. I'll quickly do it on the board again for you. Okay, let's just have a look. Right, I'm going to put this word absolute zero up again. Okay, now the word absolute zero represents the lowest temperature, the theoretically lowest or theoretical lowest temperature at which all energy in the system ceases. Now what they've done is on the Celsius temperature scale, which I'm going to call degrees Celsius, it's worked out to be approximately minus 273 degrees Celsius. Okay? It's minus 273,15, but let's just drop the 0.15 for ease of calculation. Now, the Celsius scale was developed by a person by the name of Celsius. Okay? And he said, let's make that lowest temperature, well, when they worked it all out, on his scale, it came out to be minus 273 degrees Celsius. The absolute temperature scale talks about absolute zero. Now, I think a lot of you guys might have heard of the term absolute zero. All right. What that means, it's at that lowest temperature. In other words, we cannot get lower than minus 273 degrees. That's when all energy in the system has been removed. So they said, okay, let's now introduce the new temperature scale, which Lord Kelvin did in the 1800s. And he said, let's make that zero. Okay, so absolute zero is zero. So in the Kelvin temperature scale, minus 273 degrees Celsius became 0 Kelvin. So in other words, everything related now from absolute zero is going to be an increasing value in Kelvin. But how do we do that conversion? Well, the conversion, T represents my absolute temperature scale. We know that the difference between Celsius and Kelvin is 273. I mean, it's quite easy to see. Whoops, I moved that around a bit there. You can quite easily see that the degrees Celsius and the Kelvin scale is a difference of 273. So all we have to do to convert from Celsius to Kelvin is take the 273 and we add the Celsius temperature to it. It's all we have to do. And we've now got a Kelvin temperature. So if I've got, for example, what's the temperature in the studio today, India? Probably around about 25 degrees, huh?
Definitely, it feels like
well,
it.
Let's say 30. It's quite warm at the moment.
Let's say it feels 30.
Right, so let's make it 30 in the studio. All I have to do is add 30 to 273. And guys, you don't even need a calculator for this. Well, I hope you don't need a calculator. And it comes to 303 Kelvin. And that is the absolute temperature in the studio at the moment. That's the temperature you have to use in your calculations. Okay.
Fantastic. Okay, let's see what else. You know what? It almost feels like it's the end of the show. I can't believe it. Grade 11s, it's far too early. I'm sure we're missing half an hour. Grade 11s, thank you so, so much for tuning in. Grade 12s, don't forget that you're next. And remember, keep learning more, learning extra. See you next week, Grade 11s. Bye.